In an automatic transmission car, you will not find a clutch pedal. The transmission automatically shifts up or shifts down to the next higher or lower gear according to the amount you depress the accelerator pedal and the speed of the vehicle. Now you might wonder just how an automatic transmission transmits the engine power to the drive wheels, and just how it automatically shifts up or down. This video presentation will provide you with a basic understanding of the automatic transmission and will focus especially on these two common questions. This automatic transmission is designed for a front-engine, rear-wheel drive car. And this is an automatic transaxle for a front-engine, front-wheel drive car. These two transmissions look very different from each other, but they operate in basically the same way. An automatic transmission consists mainly of three sections, each having its own particular functions. The first section is called a torque converter. Torque, or turning force, generated by the engine is amplified by the torque converter and then transmitted to the planetary gear unit. The next section, the planetary gear unit, receives input from the torque converter and changes its speed and torque according to driving conditions. And the other section of an automatic transmission is called the hydraulic control system. It is designed to control the operations of the planetary gear unit. Now, let's review the function of each of these three systems in more detail, starting with the torque converter. This is a torque converter. The torque converter consists of the pump impeller, the turbine runner, and the stator. The pump impeller is integrated with the converter case, which is in turn connected to the crankshaft of the engine. The turbine runner is splined to the input shaft of the planetary gear unit. The torque converter itself is filled with automatic transmission fluid. We will do a little experiment now and see how power is transmitted. This is the pump impeller. Let's pour some fluid into it and see what happens when we turn it. As you can see, the fluid runs along each blade and the case. Then the fluid is flung out and away from the pump impeller. This is due to centrifugal force. Now, what will happen if we position the turbine runner so that the fluid from the pump impeller hits it? Yes, the turbine runner starts to rotate. In other words, power is transmitted from the pump impeller to the turbine runner by the fluid. This is the principle used by the torque converter to transmit power. In an actual automatic transmission, the torque converter is sealed tightly and filled with fluid. Next, let's see how this fluid moves to transmit power and amplify torque. As we saw in the experiment earlier, The fluid coming out of the pump impeller hits the blades of the turbine runner, and this causes the turbine runner to begin rotating. Now, what happens when the fluid returns to the pump impeller from the turbine runner? Uh-oh, the fluid is hitting the pump impeller from the wrong direction, isn't it? Won't this interfere with the rotation of the impeller and reduce torque rather than amplify it? Don't worry, we can solve this problem by placing a stator between the pump impeller and the turbine runner. As you can see here, the stator changes the direction of the returning fluid so that it matches the direction of the pump impeller. Now, the pump impeller is being rotated by two forces moving in the same direction, one from the engine and the other from the fluid. This causes the torque converter to amplify the torque from the engine. As the pump impeller keeps rotating, the turbine runner also rotates and gradually reaches the speed of the pump impeller. When this occurs, the returning fluid hits the back of the stator blades. The stator is now blocking the flow of fluid. To prevent this, the stator is fitted to its shaft via a one-way clutch. The point at which the stator begins idling is called the clutch point. Once the stator reaches the clutch point, the torque converter acts only as a fluid coupling, meaning that it does not amplify torque, but only transmits torque. This shows how the torque converter transmits engine power to the input shaft of the planetary gear. We will now proceed to the planetary gear unit. The planetary gear unit consists mainly of several sets of planetary gears and several clutches and brakes. A planetary gear set consists of a sun gear, pinion gears, a planetary carrier that connects the pinion gears, and a ring gear. Let's study a model of a planetary gear set to find out how it works. This is a stationary sun gear, around which pinion gears, connected by a planetary carrier, are rotating. Now we add a ring gear, which will start rotating in the same direction as the planetary carrier. The ring gear rotates faster than the planetary carrier. Next, let's keep the sun gear from moving and let the ring gear rotate instead. The planetary carrier will start rotating at a lower speed than the ring gear, but in the same direction. Now let's allow the sun gear to rotate. Let's add the pinion gears, but hold the planetary carrier so it will not rotate. Finally, let's add the ring gear. The ring gear will start rotating in the opposite direction as the sun gear. What will happen if the sun gear and the ring gear rotate in the same direction at the same speed? The planetary gear will rotate as a unit. As we have just seen with the model, a planetary gear set can do many things. Depending on which gear is turned and which is held stationary, it can accelerate, decelerate, or even reverse the direction of rotation of the output gear. The planetary gear itself can also rotate as a unit. But exactly how is this done? The clutches are used to determine which gear will be allowed to rotate to actuate the planetary gear, and the brakes are used to hold particular gears so they will not rotate. In most models, wet multiple disc type clutches and brakes are used. Take the clutch, for example. Each clutch consists of several discs and plates, and a piston and cylinder. The clutch plates rotate together with the input shaft as a unit, while the clutch discs are engaged with one member of the planetary gear set. Now, what actuates the clutch? This is done by hydraulic pressure. The piston is actuated by hydraulic pressure and pushes the plates against the discs. As a result, engine power is transmitted from the input shaft to the planetary gears via the plates and discs. In the same way, the brake plates are fitted to the transmission case, and the brake discs are connected to the rotating members, such as a gear or carrier. The piston is actuated by hydraulic force so that the plates are pushed against the discs. This prevents the gear or carrier from rotating. This is a band-type brake. In a band-type brake, the brake band squeezes the brake drum, which is connected to a member of the planetary gear set, preventing the member from rotating. One other type of brake consists of a one-way clutch. A one-way clutch locks a gear or carrier so that it revolves in only one direction. The pistons of the clutches and brakes are actuated as needed by hydraulic force, which is supplied by the hydraulic control system. Let's talk about the hydraulic control system. A hydraulic control system consists of an oil pump that creates the hydraulic pressure and a number of valves and fluid passages. Let's see what is taking place in this system. In a vehicle with manual transmission, the driver up or downshifts depending on two conditions. The automatic transmission does the same thing automatically. One condition is the load on the engine, and the other is the speed of the vehicle. Hydraulic pressure is generated in the oil pump, and the amount of this pressure is regulated by the throttle valve according to the engine load. The resulting pressure is called throttle pressure. The hydraulic pressure, which is created by the oil pump, is also regulated by the governor valve according to the speed of the vehicle. The resulting pressure is called governor pressure. Throttle pressure is applied to one end of the shift valve, and governor pressure is applied to the other end. The shift valve moves to the right or to the left, depending on the difference between these two pressures. As the shift valve moves, it opens up a fluid passage, allowing the hydraulic pressure generated by the oil pump to actuate a clutch or brake piston. Which fluid passage is opened up determines the direction and speed of rotation of each member of the planetary gear set. In other words, it determines what gear the transmission will shift into. This is the basic principle of how an automatic transmission automatically up and down shifts. Now, based on what we have learned so far, let's study the basic operation of a 3-speed automatic transmission. This shows the basic circuitry of the hydraulic control system of a 3-speed automatic transmission. Hydraulic pressure generated by the oil pump is changed into line pressure by the primary regulator valve. The line pressure acts on the throttle valve and the governor valve. The throttle pressure generated by the throttle valve acts on the upper end of the shift valves. And the governor pressure generated by the governor valve acts on the lower end of the shift valves. As you can see, there are two shift valves, called the 1-2 shift valve and the 2-3 shift valve. The manual valve is linked to the driver's selector lever and determines the transmission speed range, for example, D, 2, reverse, etc. The 3-speed automatic transmission has two sets of planetary gears. They consist of the following parts: the output shaft, the rear ring gear, the rear pinion gears and carrier, rear and front sun gear, front pinion gears and carrier, and finally, the front ring gear. These are the planetary gears of the A130 automatic transmission. This is a model of the A130 planetary gear unit. In this model, the light blue color designates the front planetary gear, and the green color designates the rear planetary gear. This is the input shaft, and this is the output shaft. How does it work? When the driver wishes to start the car moving, she moves the shift lever to D. And the fluid passage to clutch C1 is opened up by the manual valve. So clutch C1 is engaged and power is transmitted from the input shaft to the front ring gear. Since one-way clutch F2 prevents the rear carrier from rotating, the rotation of the input shaft is transmitted to the output shaft, but the speed is reduced by the front and rear planetary gears. This is first gear. As the vehicle's speed increases, the governor pressure, acting on the lower end of the shift valves, gradually increases. When the governor pressure becomes larger than the throttle pressure acting on the upper end of the 1-2 shift valve, the 1-2 shift valve is pushed upward by governor pressure. Also, in addition to the fluid passage to clutch C1, a fluid passage to brake B2 is opened, causing brake B2 to be actuated. When brake B2 is actuated, it holds the sun gear via one-way clutch F1. Therefore, the input speed of the front ring gear is reduced by the front planetary carrier, and the transmission shifts into second gear. At this time, the rear planetary gear idles. As the vehicle's speed increases further, the governor pressure also increases. And pushes the 2-3 shift valve upward. As the 2-3 shift valve is pushed up, it opens up another fluid passage to clutch C2. When clutch C2 is actuated, the input shaft is connected to the sun gear. Since power is transmitted simultaneously to both the front ring gear and the sun gear, the front planetary gear begins to rotate as a unit, but does not change input speed or torque. In other words, the input shaft is connected directly to the output shaft, which is the same as saying that the transmission has shifted into third gear. In third gear, the rear planetary gear idles, as you can see here. When the car begins climbing a hill in third gear and its speed decreases, the governor pressure decreases also, and the 2-3 shift valve moves down. The fluid passage to clutch C2 is blocked as a result. Disengaging the sun gear and the input shaft, so the transmission downshifts into second gear. Now, supposing the transmission is in third gear and the driver wishes to accelerate the car quickly, so she suddenly steps on the accelerator. When she does this, the downshift plug moves up. Opening up the fluid passage leading to the upper ends of the 1-2 and 2-3 shift valves. This pushes the 2 shift valves down and opens up a fluid passage just like in the case of first gear. So the car downshifts into first gear. When the driver wants to back up, she moves the shift selector lever to reverse. And the manual valve opens up fluid passages to both clutch C2 and brake B3. When clutch C2 engages, it transmits the rotation of the input shaft to the sun gear. At the same time, brake B3 holds the rear planetary carrier, preventing it from rotating. So, the rear ring gear and the sun gear start rotating in opposite directions. This in turn causes the input shaft and the output shaft to begin rotating in opposite directions. As you can see, the rear planetary gear set does not idle in this case. When the driver sets the selector lever to 2, the manual valve opens up the line pressure passage to the 2-3 shift valve and 1-2 shift valve. When the governor pressure increases, the 1-2 shift valve is pushed up, opening passages to brake B1 and B2, and the transmission upshifts into second gear. In 2 range, the transmission cannot upshift into third gear even if the speed of the vehicle increases, because the manual valve is allowing the line pressure to act on the middle of the 2-3 shift valve. In second gear of the 2 range, the sun gear is prevented from turning in either direction by brake B1, so engine braking occurs. In L range, a line pressure passage is also opened up above the 1-2 shift valve, preventing upshifting into second or third gear. In first gear of the L range, both the front and rear planetary gear sets are actuated, as in the case of the first gear of the D range. But brake B3 prevents the rotation of the rear planetary carrier in either direction, and engine braking occurs as a result. This brings us to the end of our presentation of the basic operation of a 3-speed automatic transmission. An automatic transmission looks extremely complicated, but if you study the different mechanisms separately, one by one, you will realize that the operation of an automatic transmission is actually based on a combination of a few simple principles.